And let's go straight to the first example. This I'm going to do from the beginning. I'm going to import the geometry of the NACA profile and set all the conditions, mesh, and then calculate and go to the post-process. So let's go to it. First of all, when you open the interface, you will see that, well, once you already know the interface, you will see that it has changed quite a lot. It's much more conceptual, intuitive, and stylish, if I may say. And the icons have been completely renewed, and there's a new color theme and new help system. Well, the first thing you find is this start data window in which we are going to choose the type of problem. Of course, there are more modules for structural analysis, keeping, and other coupled problems, but in this case, yes, the CFD module, we are going to deal with the fluid dynamic analysis. It's going to be a 2D plane analysis, fluid flow, and we don't need Stokes flow. So we just set this for the problem, and for this also you have to choose the gravity direction correctly, and all this data, of course, you can change it once in the interface because it is all in the data tree. So you can use the start data window or not because you can set the simulation type and all the settings from the data tree. So first thing we are going to do, we are going to import the IGES and IGES geometry of the NACA profile. Of course, when you import a geometry, you have to take care of the tolerance, of the collapse tolerance you are going to use, because you could be breaking some geometry which you need, or either you can skip really collapsing anything that you want to collapse, so you want to check on it. For doing so, you can go to the preferences and check in the import and export options. So you can choose to automatic collapse after import, which is, in my opinion, a little bit dangerous if you don't know very well your geometry, because of course you can, once you have imported the geometry, you can overcome these issues and you can collapse anything you need after checking. So we'll just leave it like this and proceed to import the geometry. As I say, in this case, an IGES. So let's look for the geometry. And we have this NACA profile. Some information is prompted, and we have the geometry. Of course, we have to build now the domain around the geometry. This I'm going to do quickly because it hasn't got very much interest. It's just about dealing with the CAD tools which the program has. So I'm going to build a domain around using some functions. First of all, of course, there's a lot of different ways to generate this domain. What I'm going to do is just one of them. First of all, I'm going to create a circle. Joining. Okay, so now it seems to work, and we are creating the circle. Okay, you can see here. And now I'm going to proceed to do some operations, dividing lines and deleting surfaces and creating the rest of the domain. So now I can delete the circle surface because I'm going to define a bigger surface later, and delete some of the lines which I don't need. Char this. Then I'm going to expand the domain to the right, to the positive x-axis. doing so, I'm going to copy the existing points. I'm going to extrude the lines. So let's make it to the X40, choosing to extrude lines, and I'm going to select the points. So I have this line. Also, I want to divide into faces my surface, so I will continue creating domain lines so as I can use them later for contour of the surface. As I say, I'm going to do this a little bit quickly because it's just about dealing with creating geometry, so it has no interest in fluid dynamics. So just wanted to close the domain, and that will be the boundaries of the domain. I'm going to save the model. Okay, check if there are repeated points. For doing so, I want to perform a collapse points, and checking if there could be repeated points. So here, as you can see, there were points which I didn't need, not here. So I collapsed 3 points, and I lost one here, which I'm going to create right now. Okay, so now I can generate the surfaces by contour. I just want to generate first the upper surface. One, and then lower surface, just choosing the contour lines that I need. So now I have both surfaces. Okay, so of course you may want to separate the geometry in layers. Right now we have done everything in the same layer, and I'm going to create a new one for the profile. I'm going to send to this layer the profile lines and the boundary points. So I'm going to rename the other layer and call it domain. Perfect. Well, so first thing we can do, now we are going to the problem itself, is to assign a material to the surfaces. Remember, it's a 2D problem. So we are going to use a generic fluid. Of course, you have a library with different fluids, but we are going to define a specific one. We are going to leave the same density and going to impose a different viscosity. This is set up for according with the velocity to get a certain Reynolds number for this problem. So there we go. And we will assign this fluid to all the surfaces which are conforming the domain. I choose here in the library the generic fluid, which is the one I have just modified, and select the surfaces, the corresponding surfaces to the domain. Okay, so a new group has been created. Of course, I can manage the groups and the entities inside these groups here in this window, and I can check what have I assigned inside this group. You can see both surfaces corresponding to the domain have been assigned. Okay, so next step, be assigning the boundary conditions. In this case, we have just one boundary condition corresponding to the wall of the profile. And we are going to fix the velocity, zero velocity. There's going to be a zero velocity in the wall. So we use the velocity fix wall, in this case, assigning to the profile. And again, another group has been created. We need more boundary conditions for the inlet velocity, which we are going to impose in this semicircumference inlet, or the inlet velocity will do. So we are going to use 10 meters per second velocity in the positive x-axis and assign it to both lines in the inlet. Okay. Another boundary condition, we are going to define a fixed pressure in the outlet. I'm going to fix zero pressure in the outlet in these lines. And that would be it. The only thing missing is to impose the boundary conditions in the symmetry conditions in the lateral lines. That we can do with the fixed velocity condition. So we are going to fix the velocity in the y-axis and set it to 0 in both lines, defining the lateral contour of the domain. Okay, so that would be it regarding boundary condition. We have defined the wall for the profile, the inlet, the outlet pressure, the symmetry conditions, and we are going to fix the initial field of velocity, going to fix to the same 10 meters per second. That will help to avoid transient states, because we want to reach the stationary state of the simulation as soon as possible. So that would really help. And what is missing is to set some information on, for example, on the turbulence model. In this case, as I said, the data inserted, the velocity together with the viscosity and the density result on a Reynolds number, which says that the flow is going to be turbulent, so we have to choose a turbulence model. We're going to choose the spiral almaras, but as you can see, there are, as I said before, there's a wide variety, and depending on the problem, you will want to use one or the other. So spiral almaras is going to be at this time. And some other more data that you want to define to get your problem ready. It's going to be the number of steps and time increment. Of course, in this case, it's all already set up in advance, but for a real, or the cases your own cases you are going to analyze, you will have to choose very carefully the time increment to be in according to the mesh size on critical or local zones and the velocity in such zones, so you can reach the required convergence criteria, like current or any other that you are using. So in this case, we will have this time increment, which will work for us perfectly okay. And well, maybe we don't need so many time steps, so just use 50. And we are going to write results every 5 steps. So I'm going to save. And one of the important things missing here is to generate the mesh, to assign the proper conditions. In this case, we are going to take advantage of the tools that allow us to define a boundary layer mesh. As you remember, we assign zero velocity in the boundary, so we are going to model numerically solve by finite elements the boundary layer. So we are going to assign boundary layer mesh 2D, and it asks for the surfaces surrounding such boundary. And of course, this is something that you need to have pre-calculated, and there are methods for doing so. And you have to insert the first layer height, which will correspond to the viscous layer height, and the number of layers. So in this case, in my pre-calculations, we have 1.0 E minus 5, and we are heading for 8 layers. Okay. Then we have to assign the lines we need, which are the NACA profile, and that would be it. So we have this boundary layer already set. We are going to also assign a structured mesh and a number of divisions to the profile, to the lines of the contour. So structure over lines and assign number of cells. In this case, we are going to assign 400 divisions to each one of the lines. And that would be it. We can save, and we have to check the meshing preferences. So we want to use an RSOF measure with normal automatic correct sizes, and which is important here, a very small unstructured size transition. This is very important in CFD analysis. And regarding the boundary layer properties, we are going to check this option, which is already checked, and that would allow us to see the boundary layer in a separate graphical layer, so we can see both meshes separately. So that would be it. And we can go and mesh the geometry. So point 1, the maximum element size, we are going to set it to 1 and generate the mesh. So as you can see, it's going to be quite a coarse mesh, but in any case, it gets generated very, very quick. You can see here the boundary layer, which has been generated with the 8 layers around. We can see it just by itself. So it's easier to visualize. You can see here the boundary layer mesh on its own, and how the mesh grows slowly with this small size transition to the bigger elements which are far away in the domain. So, well, we like this mesh. And just we have to begin the calculation, either here in this icon or here in the menu. Have multiple options, and just set it to calculate. You can visualize the information on how the analysis is advancing, time steps, and of course there's some more important information which you want to see during the analysis, which is how the pressure or the integrated pressure on the boundaries are advancing in time. So you have this forces graph option where you can see how the pressure is converging to an average value. You can actualize it, so you can check whenever the analysis has already converged to an average value, which will mean that your analysis can be finished. But in any case, we are going to let it finish to the 50 steps. And of course, if the analysis has ended and you see that the pressure has not converged, there are options for relaunching or recalculating from the last step that has been written. So you can you can launch again the analysis and check if more steps are needed. Okay, so it has finished. Let's see how the forces graphs. You can see here is quite smooth, but in any case we can do a zoom of such zone and see that although it's a little bit oscillating, the oscillations are getting smaller and converging to a single value. Okay, so we can give it as a good value and we can see the results. And of course you can see other forces in the y-axis, the static force, the viscous force. This will be the all summated, all added up. So let's go to the process in a second and see the results. And then quickly to the other 3D example, which will be much more quick. It's already calculated. I don't want to bore you. So we can see, of course, the velocity results and the velocity field around the profile. Of course, we can check the pressure, the contour field of the pressure, and we can see the evolution of the pressure in the whole field, as the contour field, or even we can check on some specific point and get a time graph or of the result we want, in this case the pressure, a time graph of the evolution of the pressure in such a specific point. Okay, so this can be done with any result and in any point. So of course we can also see a map of the eddy viscosity corresponding to the turbulence, and in this case we can see, for example, another visualization of the velocity near the boundary layer, and we are going to check on the vector distribution on the boundary layer. Okay, so you can see how the velocities, the field of velocities near the boundary layer is being solved.